So today we talk about combinational logic, which is CL in computer architecture. And we can start with the truth table and AND gate. So here's the switches. Here's a switch, which is the basic component in the circuit, and you have two switch here and one bulb here and the battery here. And it's basic, like if you put both of the switches connected, then the bulb is working, otherwise the bulb is not working. And if you put a box here, like this is a black box, and you got a two switch out, and you got a battery here, you got a bulb here as out. This is in one, in two, and this is out. So you can find that if in one and in two, when both of them are connected, and we say like when the switch is connected, we say it is one, and otherwise it's zero. Okay, and only when the two switches are connected, there are two ones as input, then the output is one, which means the bulb is working, and otherwise the output is zero. So this is the truth table. The truth table is just like there are two input, there are one output, and only when like the two input are one, then the output is one. And the truth table is like listing out all of the possible situations. Like, have you learned this before? Like gate or circuit?
Yeah.
Okay, that's cool. So this is an AND gate. So if you put this black box, like this black box become like this is an AND gate. And there are two input and one output. Yeah, that's very easy. And we review some circuit basics first. So this is a circuit, and this is the resistance, and this is also the resistance. They are the same, just two notation. And this is the bulb, this is also the bulb. And the thing on the left, which is very familiar for like high school students, and this is also the same as left, and this means the battery, the positive side. This is the negative side, which is the ground, and the battery to the R to the bulb. So they are the same, and only when suppose they have the same resistance. So this is 5 here, this is 2.5 here, this is 2.5 here, this is 0 here. So only when the voltage at the both sides of the bulb are different, then the bulb is working. Is that clear?
Yeah.
Okay. So let's go to transistor. Okay, so transistor is just another format of switch. Switch is too big, and your computer have some endless switches inside it. If you use switch, then your computer is too big. Cannot put it in the bag. So you use transistor. It's just very, very small switches. So this is a transistor. And the way it works is it has three terminal B, C, and E. And only when B is larger, the voltage at B is larger than the voltage at E, then C and E are connected. And if the voltage at B is equal to the voltage at E, then the C and E is not connected. So it's just a switch between C and E. and usually the E is connected to the ground, which means that E is always 0, and so that means this sentence can become this, like when B is high, then C and E are connected, and otherwise C and E are not connected. So by the way, in actual circuit, say the voltage is 5, and if you're connected to the ground, then you become 0. In computer, this binary is only 1 and 0, so if you're connected to the ground, then you're 0. Otherwise, no matter whether you are 2.5 or 5, you are 1. So that is saying, like, if B have voltage here, then C and E are connected. Otherwise, C and E are not connected. Is that clear? Like, say here's a switch, and if the switch is connected, then this thing is connected. And B is larger than E, then C and E is connected, then the bulb is working. And otherwise, if the switch is not connected, then this is not connected, then B and E is not connected, then C and E is not connected, then the bulb is not working. Is that clear?
Yeah.
Okay. So we can build the gate from transistor. So by the way, have you learned this before? Like the gates, basic gates?
No.
No? Okay. So we just mentioned the AND gate. It's a black box. There are a lot of transistors, maybe 2 or 5 transistors inside it, but we don't care. So it's an AND gate. So the AND gate is only when both of the input is 1, then the output is 1. And the OR gate is like as long as one of the input is 1, then the output is 1. That's AND and OR. It's literally so what is not gate is just inverse the input. Okay. Then we can build NOT gate first out of the transistor. So here is the NOT gate, and this is the resistance. This is the bulb. And if the switch is not connected, then what is the 3-terminal BCE? Then this is not connected, and this is not connected. Then it's working. The bulb is working like this. So the bulb output 1. Then switch is 0. Then the output is 1. And otherwise, if the switch is connected like this, and so this is connected, and this is connected, and so they never go there because this have some R here, but here you don't have R, so you just go here. So when this is 1, this is 0. Is that clear?
Yeah.
Okay. So you put it into a black box, like this looks like you can just put the lines like this, and the line. I mean, you can put it into a black box. Okay. And this is the output, this is the input, this is the battery. And we usually don't write a battery because everyone have the battery. So there's only input and output. This is input, this is output. And draw such a large thing is very complicated. So we just turn it become a black box, which is a circuit. So NOT gate is something look like this. This is NOT gate. And inside it is this stuff. Is that clear?
Yeah.
Okay. And we build AND and OR gate from transistors. We just mentioned AND gate from switches, and it's the same for transistors. It's the A and B here. The bulb is here, and only when both of them are connected, both A and B are high, then they're connected, then the bulb is working, otherwise it's not. And this is the truth table, this is the gate notation. So inside the gate is this. Is that clear? And OR gate is just like this. So one of the transistor is connected, then it can go to the ground, then the bulb is working. And so the truth table is 1 of A and B is 1, then the output is 1. And this is the OR gate. Okay. And then it's the XOR gate. The XOR is saying like the number of 1 from the input is odd, then the output is 1. So you look at the truth table. So when there is 1 in the input, then the output is 1. If there are 2 ones in the input, then the output is 0. So say we have 1. So the XOR can also be written as this. So 1 XOR 0, XOR 1 XOR 0. So there are 2 ones in the input. It's an even number, so the output is 0. And if like there are 3 ones in the input, then the number of 1 in the input is odd, which is 3. Then the output is 1. Is that clear?
Yeah.
Okay. So how do we build this? It has 5 transistors and it's a little complicated. And the notation is like this. So this is OR gate. You put stuff here, then it's XOR. Let me think. So if A and B are 0, then the output is 0. We can check it here. So both of them are 0, then this is not connected. So the bulb is not working, right? And if A is 0, B is 1, A is 0, B is 1, A is 0, B is 1. So this is connected to here. And this is not connected. So they go here. And so this is connected. And so this is connected. And you know this side is 5 and this is the R. And if 5 is connected to the ground, then this is 5, this is 0, this is 5, this is 0, right? And it's connected to the ground. This is 5, this is 5, this is 2.5, this is 0. So the voltage at both sides of the bulb is different, so it's working. Is that clear?
Yeah.
Okay. And if A is 1, B is 0, it's similar, I guess. Yeah, it's similar as these are similar. And if both A and B are 1, so this is connected. So this is like an OR gate. So this is connected to here, and this is connected to the ground. And so if this is connected to the ground, then this is 5, this is 0, so this is 0, and this is 0, so this is not connected, and this is not connected. And so it's like this. So at both sides of the bulb, there are 5. There are no voltage different, so the bulb is not working, and it's 0. Is that clear?
Mm-hmm.
Okay. So that's how you build a XOR gate. You can just put them together as input 1 and put them together as input 2 and put this as output. Then you get an XOR gate. So we just introduced the AND or NOT and XOR gate, and we just we firstly we now go from the transistor level to the gate level, which is another level of abstraction. We do not care about what's inside the gate now. So they're just gate, and the transistors are too complicated. So we just use gate for notation as the basic unit instead of transistors. And not AND, and some other stuff, not AND and not OR, they'll just flip the output of AND and OR. So not AND is like zero, here is 0001, and not AND is 1110. Similar for OR. And their notation is also just add a small circle, and like the circle means not. And just to remember how to write these 4 basic gates, maybe 5. So AND is like this, OR is like this, NOT is like this, XOR is like this, not AND is like this. Yeah, and okay, so next we introduce something called Boolean algebra. So Boolean algebra is just we want to express the gates into mathematical notation. So here A and B to C, we can just write it as, so and we use the dot as and the plus as or, and not is like this. So this is A, and this is not A. So this is C equal A and B. This is C equal A or B. This is C equal, this is B. This is B equal not A. Is that clear?
Yeah.
Okay, so this is a more complicated one, and we can write it as A. By the way, only when there's something like this means they are connected. Okay, and so for example, like something like this, only these 2 dots are connected. Like here is not connected, here is not connected. So only here is connected. Okay, and so this is A and B. This is A and B here, and A also goes here. So A and B, and this is A and B plus A here, and goes here. C goes here, and output is A and B plus A, or C, which is AB plus A plus C. And we can simplify it. There are a lot of laws for Boolean algebra. We can look at some of them. So this means x and not x is 0. So you can write a truth table of it, like x, not x, and output. So when this 1 is 0 and 1 and 0 is 0, 0 and 1 is 0. Yeah.
Yeah.
So that's the only two possible situation, and so x and not x is always 0. So you can write a truth table like this for often, and x and 0 is always 0 because you need 2 1 to get the output 1, and x and 1 is x. If x is 0, then output is 0. X1, then output is 1. So x and 1 is 1. And x is x. It's just similar. These two are the same as in traditional math. This is also not very hard. And for this, like if x is 1 or anything is 1, and if x is 0, like 0 and something is 0, and 0 or something is 0, right? And we leave the final thing out first. And for here, there are some like counterintuitive stuff. Really like this, like x plus yz equal x plus y, x plus z, and x plus y, x is x. They are like just when you use them, you can come to this table. There's no need to memorize it. And the final one is the De Morgan's law, which is you can take the not hat, like cut them and change the notation here. So x, you can just turn this to this, and you can also like this. You can also cut it into 2 and change the notation. But we're not going to use this today. So you can, with these laws, you can actually simplify this formula. Like, so a is equal to a is equal to a multiply 1, and we can use this. So it becomes a, b plus 1, and plus c. And b something plus 1 is always 1. So this becomes a, and a plus c. So you can see like this circuit is too complicated. And if you turn it, like simplify into this, they have the same truth table. Yeah, so that's the Boolean algebra. Is that clear?
Yeah.
Okay. So the next thing is canonical form. This thing is, so we usually use this as how you turn a truth table into a canonical form. That's very easy. So you have a truth table here. There are 3 input and 1 output. And you just firstly pick out all the output where it's 1. And you write the formula to express it, like 0, 0, 0, and when the three input is 0, and you just write A, not B, not C. and when the input is 0, 0, 1, so there's no not on C. So this 2 need to become 1, and this is 1. Like, how to say? Okay, so ABC get Y, and we suppose the ABC are just A and B and C to get 1. And how you get 1 with N? You need all the input to be 1, then the output is 1. So you need to flip A, flip B, flip C. So three of them is 1, then output is 1. And similarly for this, and for this, the A is 1, B and C need to be flipped. And for this, the A, B, and C need to be flipped. So there are 4, 1, and there are 4 formula here. And we OR them together. So this is AND, this is OR. So that means like only as long as one of the 4 is 1, then output is 1. So the truth table can be turned into this. It's called canonical form, and it's also called sum of products, which is the OR connected like 4 and that's very clear, I think, because like as long as one of them is 1, then the output is 1, and for this to be 1, you need to ABC be 0, 0, 0, and it just corresponds to the truth table. Is that clear?
Yeah.
Okay. So this is like how to turn a truth table into canonical form. And then we want to build a combinational logic. What is combinational logic? Like, let me think. For example, combinational logic is like a larger black box, and there are a lot of gates inside. We don't know how we don't care. Like a lot of gates inside. So it's another level of black box. And you have, so today we want to build an adder. So what is an adder? Like you have 3 inputs, 3 output. We give out the battery, and you have 2 3-bit input and 1 3-bit output, and say this is 1, 0, 0, this is 0, 0, 1. Then this is a black box, and it gives the output of 1, 0, 0, 0, 0, 1. They add together is 1, 0, 1. They get 1, 0, 1. So this means like this is 4, this is 1, and this is an adder. And it output 5. Adder for 2 binary number into 1 binary number. And this black box is called combinational logic. Yeah, and like you get from input to output, it's like immediate. You take the switch here to be 1, 0, 0 and 0, 0, 1. It's just 6 switches here. And you immediately get output as 1, 0, 1. Like here are 3 bubbles, and these 2 are working. This is not working. Okay, is that clear?
Yeah.
So this is a combinational logic. And we're gonna build it out of the gates, okay? So how to build a combinational logic? Firstly, you get the truth table for it. The truth table is just designed by human, and so you get a truth table you want to achieve. Then you turn into canonical form, like we just introduced. And the third step, you simplify it with Boolean algebra. which is something like here. And the fourth step is you write out the gate design, and we're gonna go through this one by one. Like on the example, like we build an unsigned n-bit adder. N-bit adder means like you have two n-bit input and two n-bit input and one n-bit output. This is adder. Unsigned means you don't have sign and all the numbers are just natural number like 0, 1, 2, 3. There's no negative number. That means unsigned. And signed is you have negative number like for -3, -2, 0, 2, 3. And you need to add and subtract. And do you still remember how we like represent number in unsigned first? So say that the n equals 3, then it's a 3-bit adder, then 0, 0, 0 is 0, 0, 0, 1 is 1, 0, 1, 0 is 2, 0, 1, 1 is 3. So this is 1, 2, 4. Similarly, 1, 0, 0 is 4, 1, 0, 1 is 5, 1, 1, 0 is 6, 1, 7. So 3-bit can represent 8 numbers, which is 2 to the 3. Is that clear?
Yeah.
Okay, so we want to build a combinational logic to be able to add 3 numbers, a 3-bit number or n-bit number. Okay, and so we start with this. So we go from 1 bit first, or actually this is 4-bit here. So there are two 4-bit number, and 4-bit can represent 2 to the 4, which is 16, and it's 0 to 15, 16 numbers. There are two 4-bit number. We want to add them together, and so the first bit, this is the like least significant bit or just the lowest bit. So for the lowest bit, 1, 0, 1, 0, 1, 1, and 1 plus 1. Or you can write this small one to here. They're the same. Oh. So this is carry in English, right? I don't know. And so the lowest bit you do not have to carry. And other bit, like all the other you have carry, right? So we can treat them separately first. So this is the lowest bit. You do not need to care about the carry. And so it's just A0 and B0. And 0 plus 0 is 0. 0 plus 1 is... Okay, oh, sorry. So the two output in truth table here, the S0 is like the result of adding them. And the C1 is the carry to the next bit. Okay. So 0 plus 0 equals 0, and there's no carry. 0 plus 1 equals 1, there's no carry. And the 1 plus 0, there is 1, there's no carry. And the 1 plus 1 is 0, and the carry is 1. Is that clear?
Yeah.
Okay. So for the lowest bit, we want to build a circuit to carry this out. And you can see that this is S0, this is C1. And S0, there are two 1 here, which is, this is just XOR gate. And there's only one here is the AND gate, right? So S0 is A XOR B, C1 is A and B. Then we can add the lowest bit together, right? Is that clear?
Yeah.
Okay, and for the next 3-bit, like we need to consider the carry. They all have a carry here, probably. So there are 3 input, A, B, and C. And if A and B are 0, then if A and B and C are 0, then the output 0, no carry. And if of them are 1, then the result is 1, the carry is 1. It's just similar. We just consider the carry here. So we can actually do not look at this. Let me see. This is a little confusing here. We just delete it. We just delete this. Okay, so we do that by ourselves. So you get a truth table. Like you want to add. This is the 3 input. This is the output. Like C1, C2. Like this is 3 input. This is 2 output, and you get a truth table here, right? So that's the first step, which is design the truth table. And the second step is get a canonical form. Okay, and like looking at this truth table, and we want to get a canonical form. So there are 2 output, we just treat them separately. And for the first output, which is SI, the 1 is here, 1 is here, 1 is here, 1 is here. And so to get a canonical form is like A, B, C, which is this, and plus A, not A, B, not C, which is here, and plus A, B, C, plus ABC. So this is the canonical form of SI from the truth table. Is that clear?
Yeah.
Okay. And the next step is simplify it with Boolean algebra. Simplify it. So when you look at something, this is actually A, X or B, X or C, actually. It's more like a formula. So when you look at this again, like only when the input of the number of 1 in the input, then the output is 1, right? There are 2 1, then the output 0. There's 1 1, then the output is 1. There's 3 1, then the output is 1. This is XOR. So we can just make it easier. It's just A XOR B XOR C. Is that clear?
Yeah.
Okay. And next we go to the Ci plus 1, the other output. And let me think. This is truth table. These are the ones, and we write a canonical form of the input. And it's A, C plus A, B, C, right? And simplify it. So this two, like we can go to A, B, C plus C, which is, let me look at it, which is 1. So this just become AB. And for here, we can see, by the way, this is just XOR actually. You can find they have the same truth table. And this is CA XOR B. So plus AB here. So we just simplify it. That's the third step. So is all of this clear?
Yeah.
Okay. Okay, so we have, so the final step is the gate design. And so we have I equal A XOR B XOR C. And C I plus 1 equal C A XOR B, C and A XOR B, and or A and B. Right? And we do the gate design out of it. So SI, so here's A, B, AI. The input is A, AI, BI, CI. And we just first A and B XOR, XOR, and we XOR with C, right? Or we can just write it as like this. It's also okay. And the output is SI. And we can also put a C here, put a B here, put an A here. And we do the other one, which is A XOR B first. A XOR B. This is A XOR B. And we OR with C. And with C, sorry. And with C. So this is A XOR B and C. It's a little ugly. And here's A and B. So we have A and B. This is A and B. And we want to put them to an OR gate, which is the OR here. And we output CI plus 1. Is that clear?
Yeah.
Okay, so then the final step is we put this as a black box. Black box. So there are 3 input and 2 output. And inside it, it's a lot of gates, right? And we can get like the output from the input. So this is a combinational logic. And we just say, so this is the black box there, right? Yeah, this is the black box. And inside it's like this. So A, B, C are the 3 input and there are 2 output. So this is a 1-bit adder. Is that clear?
Yeah.
Okay, cool. So that's how we get from a truth table to the real gate. Okay. And the next step is we build a n-bit adder, unsigned n-bit adder. So you can see that for the lowest bit, we just build an adder for the higher bit, and there's still a lowest bit, and lowest bit doesn't only have 2 input and 2 output, and it doesn't have the C here. So you can see that if you set the C always to 0, then it's a 1 bit as for the lowest bit. They are the same. The C is always 0. Okay. You can look at the truth table, but that's true. And so you can put the C0 as always 0. And so this is the lowest bit. Lowest bit, 2 input, 2 output. And for the next bit, it's like the C1 is the carry, and there are 3 input and 2 output. And just go all the way there to the end. And this is an n-bit adder. And you can also put this into a black box, so we only care about the A0 to AN and B0 to BN. Or actually, it's AN to an A0, BN to B0. This is the combination logic. This is black box, and we have an output, which is Sn to S0 and a Cn finally. This is always 0. So in this way, we can build an adder for n-bit number. Is that clear?
Yeah.
So an adder is here is a lot of n switches. There's n switches. You can put them as say this is n equal 4. So there are 4 switches, and 1 0 0 1 and 0 0 1 0. Then the output should be this is what is this? This is 9. This is 2, and the output should be 11, right? A plus 3, right? And the Cn is 0. So the Cn is the whether you have to carry at the final step, and it's also a tag for overflow. So what is overflow in binary calculation? So we are using our 3-bit adder. So 3-bit add another 3-bit. And if the first 3-bit is 111, the other 3-bit is 111, then it means it's 7 plus 7, and you output a 3-bit. And you cannot represent 14 in a 3-bit. Let's see how it works. So this is just circuit, okay? And circuit just do the calculation, and it's 1 plus 1 is this is this, this is this. Okay, so the output is 110, and the Cn is 1. That's how the circuit do. It doesn't care whether it's overflow. It just gives you the result. So the answer should be 14, but you cannot represent 14 in 3-bit. So what is the answer here? Actually, it's 6. So it's the wrong answer, right? So when you have the carry at the final bit, which is the highest bit, that means your answer is wrong. It means its overflow happens, and it means your bit cannot represent the final answer. This may be a little confusing. Let me think. Yeah, so for unsigned number, so unsigned means only natural number. Then if the final output here is 1, that means your result is 1. And if the final output is not 1, is 0, that means your result is right. Then you can use the result. Okay. And you may be, people may ask like, the computer can only like say the result can only be there's two 3-bit number and the result is larger than 7, then it's overflow. Like 3 plus 4 is not overflow, but 3 plus 5 is overflow. Seems like the combination logic is useless because it can only represent very small answer. But this is n-bit here, and like say n usually equal to 32, and you can actually do 2 to the 32 plus 2 to the 32. And if the answer is larger than 2 to the 32, then it's overflow. It's actually a very large number and it's very powerful. And only very, very, very large number cause overflow, right? So you can still have the right result for all the numbers smaller than 2 to the 32. This may be a little confusing. Is that clear?
Yeah.
It's just saying like when the final carry is 1, then the result is wrong. Otherwise, the result is right. Okay, and this is called the overflow tag. Okay, then we go to signed number. It's very complicated. So we just review it first. These two slides are from the last lecture, which is a long time ago. We review it. So the way we represent negative number in binary is called 2's complement. It's just like 0, 1, 2, -1, -2. This is 0, 0. This is 0, 1. This 1, 0, which is normal. And for negative part, this is 1, 1. This is 1, 0. Okay. And the reason why we represent like this is because they only have 1, 0, and they have simple circuit. And last time we do not know why they have simple circuit, and this time it's clear now. Because if you write out the truth table and you get a canonical form, and you simplify it with Boolean algebra, then you build a gate out of it. You can find that represent negative number in this way, they get very single gate design. And for the other two, they get very there were like 1's complement and sign and magnitude. There are other two ways, and they get very difficult circuit just out of design. And the simple circuit here also because that they use the same circuit with signed number, with unsigned number. So this is signed, they have negative number, and they have exactly the same circuit here, the circuit here. The only difference is at the overflow bit. Okay, this may be confusing. Let me think. So now you can write a truth table out of it. So say we have A, B, C, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, the 8 possible stuff. And so let's just use a simplified case. There's only we just care about the lowest bit, AB, and this is the output. 0, 0, 0, 1, 1, 0, 1, 1, 4 possible case. And let me think. Okay. So I want to show that like they use the same circuit as unsigned number. 0. Okay, actually it's like this. 0, 0, 0, 1, 1, 0. Three is 1, 1. No, no, no. Okay, sorry. This is very hard. 1, 0, 1, 2. Sorry, it was not. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. Okay, minus 1, minus 2, minus 3, 1, 1, 1, 1, 1, 0, 1, 0, 0. So this is the 3-bit signed number, and it can represent minus 4 to 3, which is 2 to the 3 equal 8 numbers in total. And we can show that you can do just normal add-ons, like if you calculate minus 4 plus 3, then you get minus 1, right? If you do minus 1 plus 2, then you got minus 1 plus 2. Oh, sorry. Then you got 1. We don't care about overflow. Okay. Then you got 1 here. So the benefit of two's complement is it can do add calculation the same as sign using the same circuit as sign, just the usually binary add. Is that clear?
Yeah.
Okay, sorry about it. Yeah, I hope it's clear. Yeah, it just means like when you add two numbers together, you can use the same circuit. Okay. Anyways, so just to review that, if you go from minus 3 to 3 in the two's complement, it's first, so minus 3 is 1, 0, 1, 3 is 0, 1, 1. So go from this to this, it's just flipped off the bit here. 0, 1, 0, then add 1, 0. So this is flip all the bits and add 1. And also you can go from 3 to -3. It's 0, 1, 1, 1, 0, 1. It's also flip all the bits first and add 1. So when you go to negative, it's flip all the bits and add 1. Is that clear?
Yeah.
Okay. So we build the signed adder. We just build an unsigned adder. Then we build a signed adder here. So I just showed that the add is all the same except for the overflow tag. Okay, so that means the result is the same, only the flag which indicate whether the result is right or wrong is changed for signed number. So for unsigned number, if the Cn is 1, then the result is 1. If Cn is 0, then the result is right. And for unsigned number, it's more complicated. So here is like for unsigned number 2-bit. From 2-bit is from -2 to 1, which is 4 number. And you see it here. By the way, this is so at this part, this is the same as this. So we only care about half of them. So we are adding them together, like, and 0 plus 0 is 0, 0 plus 1 is 1, 0 plus -2 is -2, 0 plus -1 is -1, which is all normal. And here we add 1. 1 plus 0, 1 plus 1 is 2. And actually 0, 1 plus 0, 1 is here and here. And you see 1, 0 is, so 1 plus 1 should be 2, but here it get like 1, 0, which is -2. So the result is wrong, and we give it a red thing. So it means the result is wrong. And for this, it's 1 plus -2 is -1. And we can do all these two out, and we can find that these two are wrong. And by the way, if it was the unsigned number, then as long as you have this, the final output here, then it's wrong. So for unsigned number, there are 4 wrong answer. And for here, it's the signed number, and when you look at them detailedly, it's only these 3 are the wrong answer. For this, -2 plus -2, and it goes 0, 0, which is 0. -2 plus -2 equals 0 is the wrong answer here. And here is -2 plus -1. It's 0, 1, which is 1, and it's the wrong answer. And you can kind of, but for this, it's -1 plus -1, which is -2. And 1, 0 is -2 is the right answer. So only the 3 red is wrong answer. Is that clear?
Yeah.
So what we're doing now is we just find an indicator for the wrong answer for the signed number. So when you look into that, like what indicate the three wrong here? So this is the carry for the second bit, and this is carry for the third bit. You can actually find that overflow is equal to the XOR of them. So if there are two 1, both of them exist, then it's not overflow. And if there are none of them exist, and they don't overflow, only when one of them exists, then it's overflow, which is just the XOR. The overflow tag equal to XOR Cn minus 1. This is Cn, this is Cn minus 1. Is that clear?
Yeah.
Yeah. So this is for signed adder. So how do we change this to signed adder? So the results stay the same, which is the benefit of the 2's complement, and the overflow bit is the Cn minus 1 and Cn. We do an XOR here, which is the overflow. So this becomes the black box, okay? This becomes the black box, and this is the overflow tag. This is for signed number, okay? And for unsigned number, it's just, this is the overflow bit. Is that clear?
Yeah.
So, yeah, so just to summarize, 2's complement give very simple circuit because they can use the same circuit to carry out the adder, and you only need to change the overflow tag, the logic of overflow tag, okay? And the final one is we want this circuit to also do subtract for signed number. Okay, this is another complicated stuff. So remember that if so A minus B, so naively we would just build another circuit out of the just like how we build the adder, we write the truth table for the subtractor, and we write a kinetic form, write simplify it, and write out the gate, and it become a black box for the subtractor. But actually, there are some very, very clever way to just modify this adder a little bit to make it both can do add and subtraction. Okay. And A minus B in signed number is the same as A plus minus B, and in signed number minus B is equal to flip all of them and plus 1. We just review it, right? Is that clear?
Yeah.
Okay, so we can do some very clever stuff here. So we want to, so it's just like there's a signal. The signal can say if the signal is 0, then we are doing add. If the signal is 1, then we are doing subtract. Okay, and when we do subtract, we are just, all the other stuff are the same. We just put the B to B, not B plus 1, okay? And remember that for the adder, like for here we're using the, anyways, we're using the signed number, And remember that this C0 is set always to 0 for the lowest bit, right? And we can actually use it as the signal of add or subtract. And if C0 is 0, then we are doing adding, which is normally. And when C0 is 1, you see like this is actually an add 1 here, right? If C0 is 1, we are adding 1 to the input. And so for this, and we also, so add 1 is here, and we also need to flip the B. So how to flip B? We just do an XOR here. So if the sub signal is 1, like it's 1 for all of them, and XOR, we just, okay, here we have the truth table for XOR, and we say this is the B0, for example, and this is the sub signal. And you see when sub signal is 0, then the B stay the same. And when sub signal is 1, then we flip the B, right? So the XOR gate here to the XOR gate for both the sub signal and the B bit is just doing like, if sub signal is 0, then B stay the same. If sub signal is 1, then we flip B. Is that clear?
Yeah.
Okay, so we have this circuit. The C0 was like kind of wasted. We set it always to 0. And now we can do some little change to the circuit. And when the sub signal is 1, then all the B are flipped it, and we add a 1 to the input. That's very neat and clever. Yeah, is that clear?
Yeah.
So, and this is the overflow tag we just introduced, Cn XOR Cn minus 1. So we put it into a black box. Then it's an adder. So what does black box look like? It's the black box, and here are the AN to A0. Here are the BN to B0, and here is a subsignal, and here is the output, and here's overflow tag. So when we put the subsignal to 0, then the output is the output here is the sum of the two input, which is as the sum of them, and the overflow tag just saying like whether they are overflow, whether the result is right or not. And for most cases it's right, and if it's wrong, then we can have a tag here. And if the subsignal is 1, then we output the SN is A0 minus B0, and the overflow tag still indicate whether the output is right or not. So this becomes a black box. Is that clear? It's a little complicated.
Yeah.
Yeah, maybe you should, like, people should go through this stuff like multiple times until they understand it. It's just a little complicated. So we actually go from the switch, which is the transistor, to the gates, then to combinational logic, such as the adder or subtractor here, signed n-bit adder or subtractor. And that's how your computer doing sub or subtract inside it. Yeah, or actually that's very complicated, and actually this is not how your computer doing it. Sorry, because it's too slow. There are other way to improve it. But we leave it. We just end here. Is that okay? Is there any place that is not clear?